Morning, everyone. So today we're going to be starting into our second main chapter. This one here will be a chapter on equilibrium. Basically, we're going to talk about what equilibrium looks like in chemistry, what are some of the math towards the end of this chapter here. This concept of equilibrium actually comes back through the remaining course, so sort of the better you understand this section here, it'll help you in the long run. So we'll just start off here. This one here will be Unit 2. Today will just be a quick introduction to what we mean by equilibrium. Sometimes to shorthand the word equilibrium, we'll just put EQM, right? So equilibrium. So for starters, before we get into the main sort of chemical equilibria that we're going to be focusing on, we're going to start off, it's possible to have physical equilibria. So this word here, physical, has to do with, remember, we're creating no new substance, right? So essentially it's a physical change. Nothing has actually, no bonds have broken, no bonds have formed. So there's two examples of this that we're going to see. First is what's referred to as a liquid-vapor equilibrium. So let's just do as an example here. If we take bromine, we know it's a liquid. Under our regular everyday exposure of it, this one here is actually a liquid. So imagine you have in a container, we have a bunch of this bromine liquid here. It's like a reddish-brown sort of liquid. What we're going to find is liquids are generally, they're going to naturally head towards a situation where it's liquid-vapor equilibrium. So one thing that we're going to see is that we have to be in a closed system, because especially as this bromine here liquid, as some of those Br2 liquid particles evaporate, they're going to end up becoming Br2. So you're going to emphasize here, nothing has changed with the diatomic molecule, but it definitely is going to be in the gaseous form. So basically some of these particles that were swimming around would be jumping out into the gas. Because we want sort of reversibility for this reaction here, if we were in an open system, the gas would just escape. It would never achieve this equilibrium. So one important note, as we're going to see in this section here, is we do want to refer to a closed system. A closed system, matter cannot escape. Right, so I want to make sure the gas sticks around so that eventually, right, so at first it was just all evaporation. Once I build up enough gas, these gas particles can actually sort of do the reverse of this evaporation and condense back into the liquid form. So we're going to just make a note here, especially going in the reverse direction here. Liquid particles evaporate into gas, so that's the forward direction. And then what ends up happening is in the reverse is gas species, they collide with the surface, and then in this case here, if you remember in chapter 5, that's a exothermic process, losing energy to condense. Right. So as gas becomes liquid, we end up using up the energy. So we're starting to introduce this sort of notation here. First thing, these arrows here heading in both directions. At the heart of it, it starts off just saying reactions are reversible. Reactions can go either left to right, right to left. Shouldn't be that hard for you to appreciate here. If you think back into chapter 6 here, we had the whole notion of endothermic, exothermic here. Although it's a little bit hard, it's not quite a chemical change here. I just want to introduce to you, well, for most of these ones here, there is a activated complex. There is a transition state that's sort of in between reactions and products. There is, sure, an energy hill going one way, there's an energy hill going the other way, but if you were an activated complex, you actually have the freedom to go either in the reverse direction or the forward direction. So in this case here, we're going to still use our general notation here. We're going to have our reactants on the left side. We're going to have our products on the right side. And especially as we go reactants to products, or when we read left to right, that's referred to as the forward reaction, or extended reaction. Products to reactants is actually the reverse reaction, just reading it right to left. So products to reactants, this is called the reverse reaction. So an equilibrium is such that the reactions could go both ways, and they've sort of achieved some sort of balance that once they've sort of hit this equilibrium here, there's no more big-scale macroscopic changes. The other type of physical equilibrium that we have here is what's referred to as a heterogeneous equilibrium, dealing with solubility concepts. So in this case here, let's consider a saturated solution of NaCl. Right? So we'll start off here. Well, I know NaCl, I know it's table salt here. In fact, because it is an alkali salt, I expect it to be very soluble. That's true. So I start off with a bunch of NaCl here. NaCl starts off as solid. If you check your solubility chart here, this one is definitely soluble. This table salt here will break up pretty easily. So first couple things that end up happening is the NaCl, you drop it in, it dissolves. You drop more in, it dissolves. You drop more in, it dissolves. There will be a point where you've sort of maxed out the amount of sodium chloride that can actually dissolve in the solution, that any more extra that we drop in ends up solidifying out as a precipitate on the bottom. That's referred to as a saturated solution. A saturated solution here should have the undissolved material present. Basically, you have hit the solubility limit. So this word solubility here actually implies you've actually dissolved the max amount of solute given this amount of solution that we have, solute dissolved. Alright, so basically it's not that NaCl wasn't soluble. In fact, a lot of it did dissolve, but you've actually just basically filled up all the spaces left behind between the liquid molecules, and we actually just have a lot of undissolved material present. So what's in equilibrium here? The reason why we refer to it as heterogeneous is because there's actually two different states. The first one, as implied, is going to be starting with NaCl here as a solid. The dissolving reaction we usually treat as a forward reaction here. We know it's going to dissociate. Na plus and Cl minus is going to now be in the aqueous form. It's heterogeneous because the NaCl are dissolved in water, that form. Eventually, when we actually have undissolved material present, what ends up happening is now these dissociated ions actually collide together, and they can actually solidify back out to become precipitate. So in that case there, this is again a physical equilibrium. You could argue, yeah, there was a chemical change because a bond broke, but definitely there's no sort of replacement, there's no fancy switches in bonds. So it's just basically, it's breaking up one direction, so we call that the dissolving reaction. So dissolve is going to left to right. Dissolve is going to have matched up with going the other way here. We could call it crystallization because we're ending up forming the crystal again. But because this happens again and again, we're going to actually refer to this as recrystallization. So it happens in cycles. So even though outwardly, when you look at a saturated solution of table salt, it looks like the table salt is just sitting there. If you could actually tag some of these molecules here, you actually see, nope, the reactions are continuing to occur. The solids are continuing to dissolve. It's just that macroscopically, some of the other particles here are colliding and solidifying out at the same rate, so that overall, it looks like the total amount of NaCl here is actually unchanged. In fact, when we actually hit this equilibrium, not only do both of these reactions are available, they've actually settled out so that the rates are actually equal. So that's one key thing we're going to see in this section here. So now using that as a background here, we're going to refer more so to a chemical equilibrium system. So consider the following system here. You may recognize this reaction here as the Haber process. We use iron as a transition metal catalyst for this one. There's actually two things that are happening. So for starters, when we look at our reactants, when we look at the left-hand side, the reactants N2 and H2 collide. Remember, for a successful collision, you need to have a good energy, a good geometry collision here. They collide with those features here, becoming, so they actually break bonds, they become ammonia, NH3. So that's the forward reaction. And then the reverse direction is actually, we actually have products around. The products NH3 are becoming N2 and H2. So when we hit equilibrium, we start seeing, this is actually the symbol for equilibrium. The reaction is now can proceed both ways. Reactants can go forwards, or the products can come backwards. So the overall reaction here is said to be reversible, right? You can go back and forth. And again, we would wait. Sometimes it takes about a minute or so. Sometimes it could take hours to equilibrate. But eventually, you're going to hit this situation of balance where the rates end up being equal. So we say a system is at equilibrium when the forward reaction rate equals reverse reaction rate. In chemistry here, we refer to this aspect of equilibrium. In chemistry, we do what's referred to as a dynamic equilibrium. So outwardly, it looks like nothing is changing. So you have a container, you have a bunch of N2H2, you have a bunch of NH3. It looks like the relative amounts are actually unchanging. In fact, it's dynamic, meaning things are still occurring. We can say here the microscopic reactions. So the N2 and H2 becoming NH3, NH3 re-becoming N2 and H2. Microscopic reactions continue to occur. They continue to happen. Right? So it's not that everything is stationary and everything is stopped. And yet, when we hit this equilibrium, macroscopically, things are unchanged. So macroscopic properties are unchanged. Now, if you think about that here, how could both of those things be true? How can it be that things are still changing, and yet outwardly it looks like nothing's changing? In this case here, we have the how do we wrap those two things together is this statement here: the forward reverse reaction rate actually has to equal the reverse reaction rate. So it's not that the forward rate has completely stopped. The N2 is constantly colliding with H2. It's constantly generating some new NH3. But if the NH3 actually ends up reforming our reactants, our N2 and H2, at exactly the same rate, overall, we can still have a balance. So I use an analogy, let's say a hockey game. When you have a hockey game, let's just imagine the players on one team here. So we have 3 on the center line here. We have 2 defensemen here. I'm going to forget the goalie for a second. So we have a situation where macroscopically I have my 5 skaters on my team, right? But if you ever watch a hockey game, you realize, wait a second, every minute or so, it's not the same 5 players on the ice. Sometimes they do a quick line change here. 3 players on the ice, they switch off. There's a bunch of players that are sitting on the bench. As long as 3 players also switch on at exactly the same rate, you will macroscopically still have a 5-player hockey game. When will the macroscopic change is if I have too many players step off and not enough players to fill their spots, or vice versa. So even though macroscopically here we have a 5-player hockey game, there's constantly microscopic reactions still occur. So maybe this is like the forward reaction here. Reactants are becoming products. Our forward line is actually jumping off to be benched, and the players on the bench are now jumping off given their turn. So as long as those 2 rates are equal, we can have both of these features still true. So what's important to note here, as I just mentioned, equilibrium, EQM. Equilibrium does not mean reactions have stopped. Right? I just mentioned, well, no, they still occur, right? Constantly players are jumping on and off the ice, but we have that conclusion here. Those 2 rates are actually equal. Equilibrium does not mean reactions have stopped, but continue at equal rates. Right? For this reason, we refer to chemical equilibrium. We refer to, I already wrote it down for you here. We can say this is a dynamic situation of equilibrium. In chemistry, we're always going to do dynamic equilibrium. In physics, you're also going to do like sort of, let's balance beams held by strings. That's a situation called static equilibrium. When it looks like the beams actually aren't moving, it's really because the particles themselves actually aren't moving. So in the chemistry case here, at least, we have a dynamic situation here. For an equilibrium to exist, the system must be closed. We mentioned in that earlier example, especially if I have a reaction that ends up forming gas, we want to make sure the gas stays in close vicinity. Right? So I don't want the gases to just naturally escape, and then therefore they don't have a chance of actually coming back the other way. So we're going to study this in a little bit more detail. Let's examine what happens to equilibrium established for the simple system below. So we have dinitrogen tetroxide here forming 2NO2. The NO2 chemical is actually a brown colored molecule. So the more NO2 I have in the container, the color intensity of the brown actually increases. So a couple different cases over this next page here. Case 1 is we start only with N2O2. In this case here, as I wrote it, we're starting off only with reactants. So imagine with me here, I have a container full. All I put inside is a bunch of these N2O4s. Are we in equilibrium? Well, definitely not, because in this situation, I only have N2O4. I don't even have a product to speak of. So the concentration of N2O4 is going to start out fairly high, N2O4. The NO2, which is our brown chemical here, starts off at 0, NO2. What's going to happen over time? Well, since I have these reactants here, they're going to collide with good energy, good geometry here. They're going to steadily react to become NO2. So over time, I would imagine the NO2 is going to steadily climb. As those N2O4s converted themselves to NO2, the N2O4 would also drop. We can actually even track this mole ratio here. You see that it's a 1 to 2 ratio. So for any little bit of N2O4 that ends up dropping, we actually gain the NO2 by twice the amount. So we're going to watch our N2O4 drop. Let's imagine it drops by this amount. I don't know exactly how much it is, but if you just track how much have I lost of N2O4, this will be in a 1 to 2 ratio with the NO2. So steadily, this is what your graph is going to look like. We're going to steadily gain products and then lose reactants in this 1 to 2 ratio. What's happening here is we're plotting our concentration, we're plotting our amount, but we're plotting it against time. So at first, right, some of these N2O4s here, this one here starts breaking up. For every one N2O4 that breaks up, we're going to start generating more and more NO2. We're going to hit a situation eventually of equilibrium, because what's going to happen is we're going to have a container. I still have a bunch of N2O4, right? It hasn't dropped to 0. I now have a bunch of NO2, but now that the NO2 chemicals the concentration has sort of added up, we've actually allowed the NO2s, now these guys can actually collide with good energy, good geometry, and they can actually start coming in reverse. So what's going to happen is when we actually hit a situation of equilibrium, two NO2s are going to collide together. They're going to end up reforming N2O4. That would create more N2O4. Well, no. At equilibrium, the N2O4, every N2O4, they could collide together, they can decompose, and they can end up reforming NO2. So overall, the net in my container, maybe I have the 4 particles demonstrated here, but it's not ever the very same for NO2. The two NO2s here are becoming N2O4 as other N2O4s are reforming NO2. That's why the concentrations are actually constant in time. So you can make a note to yourself here at equilibrium. The concentration of NO2 and the concentration of N2O4 are constant. I want to be really careful here in time. So this is the time reading here. When I hit this equilibrium, the NO2 is constantly changing to N2O4. N2O4 is constantly changing to NO2. But you see that the concentrations themselves have sort of leveled off. And that's something they always like asking you when you see this graph here. What does it mean that the concentration has leveled off? That means we've actually, our system has reached equilibrium. And again, it could happen in the order of seconds. It can happen in minutes, right? Now, one thing that's not super clear here is, yes, the concentrations are constant in time. Yes, macroscopically, nothing looks like it's changed. What I want to compare here is the NO2 concentration equal to the N2O4? Now, we said they had to be equal in time. So the amount over time as you run the clock can't change. But are the actual amounts the same? Well, definitely no. The NO2 is actually a lower amount than the N2O4 based on the picture that I just drew. So in general, these two things don't have to equal. So it's sort of like saying in the hockey game here, all right, we have a 5-player hockey game. Just because I have 5 players on the ice, 5 reactants, doesn't mean I have to have 5 on the bench. I can actually have 20 players on the bench here. We can still be in equilibrium. We can still manage this changing rates. So 3 go off, 3 come on. But the number of players on the ice does not necessarily have to match the number of players on the bench. So just be careful. The concentrations, they don't have to equal each other. They just have to remain fixed in time, right? So in this case here, we started off, I mentioned it's the NO2, that's this brown coloration. So we started off with a colorless container. This was just reactants only. And basically what ends up happening is the reactants hit equilibrium. As I first generate more NO2, it's going to create a sort of brownish colored gas, but basically macroscopically that intensity won't change when we're at equilibrium because the NO2 amount stays fixed in time. As the NO2 here disappears, it gets replenished at the same time. More often than not here, we're interested in this graph here, concentration versus time. Another way of representing it is actually representing the rate versus time. And in this graph here, what we're going to be introducing is we're going to show you actually the speed at which forward becomes, the reactants become products and products become reactants. So for example, here we have N2O4 is going forwards. At first, we have a forward rate. I'm going to demonstrate that in our red case. So forward rate here, these guys, there's a lot of them. They collide with good energy, good geometry. The forward rate is a lot. The reverse rate here currently starts off from 0 because I need particles of products to actually go in reverse while I don't have any. Over time, what happens to the amount of N2O4? But we just said the N2O4 is going to steadily drop as it becomes NO2. So if I have less particles, there's less frequent collisions, there's less chance of a good collision, the forward rate is going to steadily drop. As I slowly pick up more and more NO2, these guys here can start colliding with good energy, good geometry here. The reverse rate here does end up climbing, and eventually we're going to end up with a situation where those two rates are equal. It's not that either of the rates are 0. It's not that the forward reaction has stopped or the reverse reaction has stopped. Both rates continue. Let's make a note here. So both rates are still happening, continue, but at equal size or equal magnitude. So as the NO2 is becoming N2O4, so the N2O4 is becoming NO2. Right? So just introducing to you some of these concepts of equilibrium here. So this is case number 1. We start with pure reactants. Let's flip over the page here and let's study the exact same system, but let's start off with products and let's see what happens. So I'm just going to rewrite the chemical here so that when you flip the page, you still have it. Right? So what if I start off with just NO2? Now, for sure, you can call NO2 here, well, they're the reactants of the reverse reaction. But just for simplicity, hey, this is still on the right-hand side here. We're just going to say we have products. So I start off with my container. I pump it full with NO2. There's a ton of this NO2 here in my container. I don't know exactly how many I put in. Remember, NO2 is the species that actually shows a brown color, so the intensity of this here will be a deep, deep brown. So what's going to happen here is this time, my NO2 concentration actually starts out very high, and then my N2O4 is actually starting out at 0 because I'm not beginning with any of it. So starting out here only with products, over time what's going to happen? Well, the NO2s are going to naturally, they're going to collide. The lucky ones that collide with good energy, good geometry here, the NO2s are going to steadily start creating N2O4. So that made some N2O4. That made some N2O4. Right? So the NO2 concentration is going to steadily drop. I'm going to lose NO2, and I'm going to slowly gain N2O4 in that very same 1:2 ratio like we said earlier. It's totally possible that based on my starting amounts here, these lines here could actually cross each other. So let's actually do that. Let's say I'm at a temperature where I actually lose a ton of NO2. Maybe I need to drop it a little bit here. I lose a ton of NO2. And when I actually gain the N2O4 in that 1:2 ratio, it's totally possible that this line here can actually sort of cross each other. But if I just track the change here, that's a sort of 1:2 ratio. The N2O4 would actually have dropped by twice as much because of this 1:2 ratio here. So totally possible that these concentration lines might drop depending on the starting amounts, but eventually we're going to hit a situation, again, concentrations are constant in time, so at this time t and onwards, we've actually hit equilibrium. We end up settling out into a container, which is at equilibrium. We have still some NO2, right? So still a little bit brown, but it's not going to be as intense as it was before. I've now generated a whole bunch of N2O4s. The reactions continue to occur, so the N2O4 is going to steadily become NO2. That still happens as these NO2s here are going to start colliding to reform N2O4. Macroscopically, the brown color intensity here doesn't change anymore. This time, it's the reverse reaction rate that's actually starting off because I start off with just NO2. I don't have any reactants. So the reverse rate starts out somewhere here, and as this one here steadily drops off, as I lose NO2, the forward rate then picks up. The forward rate here starts off down here, and the forward rate just picks up. The rates themselves have to be equal. They continue to occur, but as reactants become products, products become reactants at exactly the same speed. So the conclusion we made out of these two cases here is equilibrium can be reached starting from either reactants, like we did in case 1, or products, right? Or even some mixture. And what we're going to find here, usually when we study equilibrium systems, we want to be at a constant temperature. It's not that you couldn't change temperature. We'll do that later on in this unit here. But if you change temperature, you actually reach a different equilibrium at a different temperature. So we want to typically keep our temperature constant so we can study just this equilibrium that we're interested in. So just a conclusion for this section here, this table. Some features of equilibrium reactions. Our equilibrium systems are dynamic. So we can say here our reactions continue to occur. It's not that really the forward rate and reverse rate have stopped, but they just have to equal each other. The forward rate has to equal to the reverse rate. The line changes have to occur at exactly the same speeds. They have to be achieved in a closed system. So especially there would be no gas lost to the surroundings. So in this system we were dealing with here, the N2O4 here was a gas, and the NO2 was also a gas here. If we were in an open system, any of these NO2s and N2O4s here might actually have sort of gotten lost, and that wouldn't end up hitting equilibrium. So in this case here, we want to make sure we're closed. Even if we're dealing with gases, they're all stuck here, so they have a chance of doing forward or reverse. In terms of the concentrations here, we say they're constant at equilibrium. I want to emphasize here, again, concentrations don't change in time. So as you run the clock here, the amount doesn't change, but the concentration of reactants does not have to equal concentration of products. So they're not equal to each other. Right? So they have to stick the same macroscopically. Overall can't change here, but they don't have to equal each other. So that flashes out a little bit here. Then macroscopically here, outwardly, there should be no observable changes. So that's what we mean by, oh, we've hit some sort of balance. No observable changes. Since macroscopic depends on the concentrations, and we already said concentrations stay constant in time. So I gave you the example, NO2 here shows a brown coloration here. When the system has reached equilibrium, it's not going to intensify in the brown color, or it's not going to get lighter or brown color here. The brown intensity will change, although depending on what temperature you're at, you may be at a different equilibrium. Equilibrium can be reached from either direction, so we're going to hit the same equilibrium, the same EQM, starting from pure reactants, like we did in case 1. We just put in the container here just the reactants, so just a forward reaction is occurring from pure reactants or pure products. It could even be some mixture, right? Some mixture of reactants and products. We're going to naturally hit the same equilibrium, and this is the conclusion, not immediately obvious, but we're going to hit the same equilibrium for the same temperature. As long as the temperature is the same amount, doesn't matter if you start off with all the left side or all the right side, you're going to end up hitting the same equilibrium. Right? So have another look over those notes here and start practicing through some questions. We'll pick it up from there tomorrow. Thanks, guys.